In a pure vacuum devoid of air resistance, a spinning football behaves as a perfectly rigid body, following exact math. It will travel in a clean, symmetrical parabolic arc, completely free of any lateral deviation. Because of its geometry, classical mechanics gives us a strict metric for this vacuum flight. The ratio of the ball's spin frequency to its precessional wobble is locked at exactly 1.67. The moment that ball is thrown on Earth, the atmosphere introduces micro-aerodynamic torques that immediately compromise this mathematical baseline. In reality, two specific anomalies occur. The spin-to-wobble ratio jumps from 1.67 to approximately 1.8. Simultaneously, the trajectory deviates entirely from the vertical plane, drifting laterally across the field. A perfectly straight, pure spiral cannot exist on an NFL field. The collision of rigid body mechanics and fluid dynamics guarantees a curved, compromised flight path. Mechanical engineer William Ray proved these anomalies exist by extracting data from actual forward passes, tracked frame by frame on game tape. This graph plots the apparent pitch angle from that tape, revealing a continuous wave-like pattern of precessional wobble. By counting these peaks against the rotation of the laces, Ray verified the spin-to-wobble ratio sits at 1.8. To verify the lateral drift, Ray tracked a series of passes aimed directly at the camera. The data shows the ball starts on a straight vector, but ultimately deflects to the right before impact. Explaining this requires moving past simple ballistics and employing a full 6 degrees of freedom rigid body simulation. This diagram maps the baseline reference frames for that math. It isolates the rotating body-fixed axes of the football from the stationary space-fixed coordinates of the field using Euler angles. Gravity alone only pulls the ball down. To explain the lateral movement, we must calculate how aerodynamic drag couples with the ball's internal gyroscope. During a forward pass, the ball traces a downward parabola. At any moment, its velocity vector points perfectly tangent to this curve. To calculate forces, physicists use aeroballistic wind axes, measuring pitch and yaw relative to that moving vector, not the solid ground. Wind tunnel data dictates that as the ball moves along this vector, the incoming air creates a strong overturning pitching moment. The air actively tries to push the nose of the ball up and backward. If a quarterback throws a ball with zero spin, it instantly succumbs to this torque, tumbling end over end and generating massive drag. Applying a high RPM spin stabilizes the mass. The gyroscopic effect takes that aerodynamic tumbling force and redirects it into a precessional wobble. To maintain this stability, the ball makes a mechanical compromise. As the velocity vector drops toward the Earth, the gyroscopic precession forces the nose down to match that angle. A football does not cut passively through the air. It actively and continuously steers its nose downward to prevent atmospheric torque from destroying its flight. This tangency requirement presents a physics problem. Pitching the nose down keeps the ball stable, but manipulating a rapidly spinning mass always generates secondary forces. For a right-handed quarterback, the ball spins clockwise. Following the right-hand rule, applying a downward force to this spin generates a reactive torque pushing 90 degrees to the right. Because the nose pitches down to track gravity, it precesses right, creating an aerodynamic sideslip. This phase plot visualizes the effect from an observer riding backward on the velocity vector. The data points cluster in the top left quadrant. The ball doesn't oscillate around zero. Its equilibrium requires the nose to point slightly up and distinctly right. Flying with the nose yawed to the right exposes the side of the ball to the oncoming air. It acts like a sail, triggering the Magnus effect and producing a sustained lateral force against the mass of the ball. The lateral drift downfield is a direct mechanical requirement. The physical act of following the gravitational curve inherently steers the nose to the side. The wide epicyclic loops seen in the previous phase plot represent the visible wobble you watch on a television broadcast. The amplitude of this particular wobble is an artifact of launch kinematics. It is driven by the quarterback's finger placement and the exact angles of attack and sideslip at the moment of release. This raises a specific theoretical question. What happens to the math if a quarterback executes a geometrically flawless release, with initial angles of exactly zero? This chart shows the simulated phase plot for that flawless launch condition. The wide epicyclic wobble is almost entirely damped out, producing an incredibly tight, condensed grouping. This vertical trace of the spin axis confirms the efficiency of a zero-angle launch. It forms a narrow vertical line, free of chaotic loops. However, a constraint remains in this pristine data. The center of this orbit still sits firmly inside the negative side-slip quadrant. Optimizing the launch mechanics can eliminate the visual wobble, but no amount of technique can erase the underlying aerodynamic offset required to keep the ball aloft. This microscopic offset in sideslip translates into highly visible macroscopic distances over the span of a football field. This table models landing coordinates for various launch angles. It proves a pristine 50-yard pass physically drifts 7 to 15 feet right of its target. Achieving maximum range requires releasing the ball with an upward and lateral bias to counteract this deflection. The aeroballistic chain reaction is absolute. Gravity curves the path, tangency forces a pitch down, the downward pitch generates gyroscopic yaw, and that yaw drives aerodynamic drift. When a long pass drops precisely into a receiver's hands, you are not watching a perfectly straight trajectory. A straight spiral is a physical impossibility. Every successful pass relies on an engineered balance of gravity, aerodynamic drag, and gyroscopic drift.